Thank you so very much for being here and for the nice introduction. Very much appreciated. I appreciate this is getting towards the end of the conference, so I'll try to make it as more fun as possible, interactive. As we were saying, the title of my tutorial is previously observing machine learning, and I put in the slides, the cover one, the link to the slides, this deck actually on Speaker Deck, and the repository we're going to use in a second. I'm going to start soon. I just want to tell you what's the plan for today. I'm going to start with this presentation, and I'll tell you what we're going to talk about, what's the plan, and blah, blah. And then we move on to the hands-on session, and we'll try to do whatever we can do together. The aim of this tutorial is to provide you an overview of the emerging technologies in this area, which is known as previously preserving machine learning. And in particular, we're going to focus on the Python ecosystem. There's lots going on actually around the data science world, but we're focusing on Python. And the approach I'm going to use is the data scientist approach. So we want to always privilege the development and the practical aspects of the thing. So whenever I'm going to throw you notions which might be new to you, I don't think I will have the time to go very much into details. Very happy to talk about it later, but not during the tutorial. Otherwise, it will be 19 hours, not 90 minutes. And the perspective will be the one of the researcher. And by that, I do mean I want to give you references and further readings and stuff you can read. And there also will be some live coding, actually. That was the intention initially. We're not going to do live coding, but we'll do coding together for sure. And why I'm doing this, this is an announcement I wanted to put into the slides. This is the very first step of my plans for a fellowship with the Software Sustainability Institute in the UK. My plan is actually to give awareness of these technologies. And this is indeed my very first tutorial. So you're the first audience I have. And I very appreciate your time today. And which means, from my perspective, whatever sort of feedback you might have, for me to improve what you're going to listen to, that would be awesome for me. So thank you very much for that in advance. Since I didn't know the audience, and let me just start with a question. How many of you are familiar with PyTorch and deep learning terms? Okay, so for those attending online, it's the majority of the audience. So is it me doing this? Sorry. And that's my roundy faces getting in the way. I will be very quick then on this warm-up, since I know really the audience. I'm going to give you just a very quick overview of the main things I assume you know already. So some of the terms in the deep learning things, epochs, tensors, parameters, hyperparameters, loss optimizer, all these terms should be shouldn't be new to you. If they are, please let me know. We'll be using this like bread and butter later. And in case you want an overview of what's going on with the deep learning thing in the Python ecosystem, well, in the Python Zen, in the Zen of Python, we can say that there's one, and there should be preferably one way to do it. We know that in deep learning frameworks, this is still not the thing. We might say that for machine learning with scikit-learn is essentially that, although scikit-learn is not the only tool, of course, but it's essentially the standard or the most popular one. In deep learning thing, there's still plenty of solutions, although I want to highlight what this is actually a slide which is old more than 3 years, as 2018 actually. And this thing is actually improving, and we indeed had a very interesting talk in this conference about data APIs, standardization of n-dimensional arrays, and this is exactly one of the important use cases that standardization might be useful. So going towards having the same, different frameworks, but indeed the same API, which makes transition from one to the other very, very cool. And in fact, this Twitter from François Chalet, a creator of Keras, was essentially showcasing 4 different frameworks to do exactly the same thing. And you have to really, really be careful in understanding what the very details in it to really understand which is which, essentially. So they look very, very similar. And it's going towards that direction of standardization then. In the deep learning, we have two main family of frameworks. We have static graphs, dynamic graphs. Static graph, you have one static graph in memory, and it goes. The graph is important because it will be part of the computation we're going to run. And so you have to keep in mind that whenever there's a deep learning model going on, there's a graph and a computational graph which is being sent and processed somewhere. Dynamic graph frameworks are actually creating this graph for every epoch, as in the animation. PyTorch belongs to this family, and so the backward propagation works slightly different, and the static graph is just like you have the graph. You can backpropagate it. In dynamic graph, you typically record whatever you're computing and you replay backward to apply the optimization in loss. Very quick rundown on main features of PyTorch. NumPy-like API, again, very good of having standardized API for NumPy-like objects like tensors. You can convert tensors and ND arrays. You can have either way. You can have CUDA support, which is brilliant. And whenever we're going to define a model, we're going to have a class which is extending an n.module. So whenever you have to define a model in PyTorch, you need to extend an n module. You have to implement the forward method, and that's it, essentially. And so in the constructor of the class, you have the definition of layers, which are the tensors. And then to complete the learning step, the training loop, you need to define the optimizer, zero the gradient, and define the loss you want to optimize. And last but not least, you also have support for dataset and data loader, which is brilliant. Fantastic encapsulation in the Python data model. We had talk about that later, yesterday indeed. This is an example of Cypher using Torch Vision, and we'll be using something like that. Good. Now, finally, let's talk about privacy very quickly. And what's the deal with privacy? The thing is that AI models are indeed data hungry. And so the more data you have, typically, the better to you, the better the model. And the thing is that there is indeed a push in the community for high quality and curated data set. The problem is when this data set contains data you're not allowed to see, so data that you cannot process because they're sensitive data. And so there might be different solutions. The first thing and most obvious thing you can come up with is, okay, I have data and I can put data and models in silos. They will be locked up and will be controlled whatever processing we're going to do with that. This is actually very impractical, to be fair. And also, one of the most popular thing to do is to apply what is called anonymization techniques, or maybe data should account for privacy. The thing is that normal anonymization technique might be leaking information, and this is just one of the many examples I can give you. The very popular one on the right-hand side of the slide, actually the left-hand side for you, is the robust anonymization of the Netflix Sprite dataset. It's a very popular paper, actually, and the thing is that this is a showcasing of an example of what is called linking attack. So you can, even if the dataset is indeed anonymized by itself, you can link external dataset to leak external information, and that was actually part of a competition, very interesting. And so more advanced techniques are actually needed, and we'll try to talk about it later. So the very first idea I want to throw in here is why don't we allow analysis without moving data from their own silos at all? And this is essentially leading to what is called federated learning. Federated learning is a wonderful paradigm, actually. It's a protocol of communication. And the idea of federated learning is that you have data not moving at all from the different owners. So you have nodes in this network which owns the data, and all you need to do is essentially sharing the computation you do on your own data. So there's this accumulating cloud there, which is getting all the computation from the many, many clients. And honestly, this paradigm worked not specifically for federated learning, for privacy initially, but it was the model that Google was using to train model on different mobiles. That's why you see mobile phones there. And so now the question is that it? So is federated learning the solution to rule them all? The problem is that the answer might be, will be no, of course. Otherwise, we wouldn't be here talking 90 minutes about federated learning. And the reasons are manifold. I'm going to show you two examples we're going to see later practically. One is that models are vulnerable. And one of the most popular examples you might probably already know is what is called adversarial examples. So you can perturb the data, you can change the input data to the model in order to make the model to make mistakes in predictions. And the reason why you want to do that may be many, actually, depending if you're a malicious user or you just want to test your model. It doesn't really matter, to be honest. The thing is that models may be tricked. And this is a very simple case. It's kind of a popular one. As in, you have this input image, which is correctly classified as panda, and then you modify with some noise, which is actually carefully selected, and then you come up with the last image that you cannot perceive as changed, actually. And this is the trick with the adversarial examples. Humans cannot see those being tampered, be changed, but the model will, of course, notice that, and it will classify it as a given. This is another very interesting one, and this is called model inversion attack. We're going to work on this specifically. This is taken from a paper, and this is also exposing another quite important vulnerabilities in models. This is taken from a paper, and let me be clear, here, this is not the generative model. So the picture on the right-hand side is the original photo. The figure on the left-hand side, or probably the right-hand side, sorry, the blurred one, has been extracted from a trained machine learning model, which was not a generative model. So it was not a model trained to generate data. It was a model trained to classify faces. This is a popular one. This is back to 2015. But this showcases you the fact that you can actually leak sensitive information. Imagine if this image was actually a medical data set, something you absolutely don't want to share with anybody because it's super sensitive. It's the definition of sensitive data, all right? And so we have to be aware about these things. And there's also another bit. Further learning requires encryption if you want to implement it. Because encryption actually is everywhere. It's in the communication on the channel, because if you transmit the data on an insecure channel, actually, you don't want to do it. But we want to do an actual step further, and we want to make the encryption to be smart in the sense that we want to get encrypted data. We don't want to decrypt the data because they're going to be sensitive, but at the same time, we want to make computation on this data. And this is actually a technique called the homomorphic encryption. We're going to see that in action later on. But just throwing you definitions you might be find familiar or not. Just let me know in case. Homomorphic encryption is an example of the paradigm is an example of asymmetric encryption in which you have someone holding a private key and a public key. The public key is the one used to do the encryption, and the private key is used to do the decryption. And this is essentially the interesting bit here is that you can process encrypted data without deciphering it, and you can actually do computations. This is the interesting bit. So whenever it comes to machine learning, it's always a matter of multiplications, summations, and stuff like that. You can do that on encrypted data, and the decryption of the result in the ciphertext is going to be exactly the same as it was in the plain text. This is the brilliant one. And last but not least, in the context of previously preserved machine learning, we cannot mention differential privacy, which is nowadays the standard for previously preserved machine learning method, which is based on a different assumption. I'm not going to go very much in details of this, but the assumption is that instead of doing any encryption, you start is based on the idea of plausible deniability. And differential privacy is a system for public sharing information about a data set by describing the pattern of the groups without sharing the information about the individuals, which is most of the time what exactly we're aiming at. And to give you a very practical and effective example, let me just introduce you to differential privacy in a way I've seen done in this video, which was actually brilliant and very on topic because this relates to something we'll be seeing later on. It's called differential privacy on PyTorch. It goes like that. So imagine you have this data set, and this data set is essentially lots of pictures, and you have a very high level of details in this image. The thing is that you can use this image as a whole, but most of the time you're interested in using, like on a single picture, but most of the time you're interested in the aggregate of the data set. And essentially what you're actually interested into using that as a whole, as an aggregate. The thing is that this aggregate contains sensitive information because it contains the faces of the people in this. So this might be private information. What if we just blur this information? And so if we do that, will that affect the aggregate? As you can see, not much. Idea of using differential privacy. Most of the time, we're not even interested in looking at the individuals. We just want the aggregates for the model training. But if we do get the individuals, we're not allowed because they're sensitive information. So why don't we get a sort of noised version of this data so that we can still compute the aggregates without leaking any private information? And I'm telling you this as a story, as a fairy tale, which makes sense, more or less. But the thing is, this framework has a mathematical proof, so you have mathematical guarantee that you're not leaking any information. This is why it's becoming the standard. And so aggregate can be counter data, computing mean, or could be complex training a machine learning model. And actually, you can apply differential privacy at different steps of the pipeline, and the gold standard now is to applying during the training. You will be seeing that, what is going to be the effect of that. Cool. So this is it. Before we jump into that, do you have any question? Expectation or things not entirely clear? Good. Okay then. So this is the repository. I'm going to open it now. I don't know if there's any. Oh yes. Oh, very quickly. What's the agenda? 3 parts. We'll try to do our best. Or probably we can jump through different bits. First part, model vulnerabilities and attacks, adversarial examples, the panda thingy, and the model inversion attack. Then we move on to federated learning. We talk about federated data, federated machine learning, so split, and then differential privacy and deep learning with model training to counterattack model inversion attack. First block, just PyTorch. Second block, OpenMind, which is a wonderful community defining many tools in this context. And the last bit is about Alpacas, which is another tool in the PyTorch ecosystem. This is the main 3 blocks of technologies we're going to use later on. Fantastic. This is the links again to the repository and to the slides if you want to. Feel free to catch up with me later on Twitter, GitHub, mail, whatever you like. Good. So first things first, let's grab the code on the repository and let me know if you have any problem. There should be, I'm going to show you directly. That's the wrong one. There you go. Okay. Now I'm going to take this, make it very big. Is that big enough? Okay. So in this repository, you may find the Get Ready notebook. The Get Ready notebook is the notebook that shows you the instructions on how to set up the environment and to test that the environment is working. I don't know if you're using Anaconda Python, which is the suggested one. If you're not, you can use there's the PEEP requirements equivalent to install all the packages in your virtual environment. It's highly recommended to set up the environment first, because especially for the second and third part, there's a specific package we may need. All right. So let me just start with that. I should have probably already going. I was wrong. Let me just start the Jupyter server. Are you all familiar with Jupyter Notebook, by the way? Is that a tool you would use to do this kind of thing? Brilliant. That was just the wrong port, I think. Why 8282? It should be 88. 888, right. There you go. Good. So if you open the get ready, is the font size big enough for you? Brilliant. So first bit, set up the environment. And essentially, this is the command you want to run. I tried to test it on multiple platforms. Not entirely sure Windows is going to work. Should be. Tried. Not entirely sure. I can't guarantee it. And I'd say then, in the rest of this notebook, you should execute the following cells. And there are a couple of cells to run to test your environment. So that if you're using Conda, there are two main commands you want to run. Conda create first, and then Conda activate PPML, which is going to be the environment called as reported in the file. The file looks like that, in case you're wondering. That's the one. A few dependencies, kind of standard one. I think the most important one to report here are Alpacas, of course, as I mentioned. PyTorch. PyTorch is going to be this version specifically because it's a dependency of Sift we're using. We're using version 05, which is currently actually not the very up-to-date. There's lots going on. For what I wanted to present to you today, I decided to go with this version. Although I will give you reference to what to do next with the new version. There's a lot going on with this PySift project, and changes are being applied. Is there anyone who's having troubles in setting up the environment I can help you with? Anything I can help you with? Oh, really? Yes. That would be interesting to report. What kind of
The source of the problem is the last dependency that you have there. This
yes, that one. Yes, this is the pack. Mm-hmm. Mm-hmm. That actually, I didn't see that coming. I'm being honest.
PyTorch as well. It's a fixed version, so that version is not available in as a PyTorch 1.8.1 is not available in CondaForge.
Okay.
For Silicon.
I'm sorry about that. That is something I will keep in mind for the future. I'm sorry I didn't this time. I don't have an M1, to be fair, as you can see. It's an old-fashioned one. And so I haven't experienced this kind of problem myself. Sorry. I tell you what. For those of you not willing to, this is something also to keep in mind for me. Sorry about that. In case, okay, I'll tell you what. One thing you can do, you can run everything on Colab. That should work. The problem, I didn't do it in the first place, is that if you go, but I will very open to suggestions about that, about the organizations of the thing. If you go to the, for example, in the very first bit of model vulnerabilities in the model inversion attack, I prefer not to saturate the notebooks with Python code, so I used external module. Sorry about the audio, which is weird. And so when you want to run this in Colab, you have to import the files manually. Normally, if you want to run notebooks from from GitHub to Colab, you have to have everything there. Otherwise, it's boring, and you have to drag and drop new files. If you're fine doing it, you cannot do any setup. You can run everything in Colab. Not all the notebooks will have this issue actually, but You can do that, alternatively.
Your repository is public though, right?
It is.
So we could git clone for the site and call that.
You can, yes. But, or you can git clone it within Colab.
Yeah.
So, oh yeah, that's something I never tried. Okay, so you don't need to drag and drop anything.
We do it for large data sets and
Oh, that's brilliant. Okay, that's even better. Good. So yeah, yeah. And does the git clone set up the environment? I don't think so. No, so you have to do it manually. Okay. So I tell you what, for those of you starting to work in Colab, I'll tell you what are the packages needed for different bits. For the first bits, you just need PyTorch, so don't worry about it. If you have running PyTorch, that's fine, and that's already available in Colab. Good. Let's get started then, if you don't mind. So I'm going very quickly about the fast Sine gradient method. I want to talk about more extensively about the model inversion attack, which is more interesting to me. Just going through this, and to show you the example here of the panda thing. There is an exercise in the end, and you're very welcome to do it on your own later. It's not really important. I just want to tell you how easy it is to implement these sort of things and also to test the vulnerabilities of models. So normally here what we're doing is the plan with this notebook. This is taken from adapted from the original tutorial in the PyTorch tutorial. I didn't invent really anything here. I just want to point you the interesting bit. We're using Linet pre-trained on MNIST, classical example. And there's something you should be able also to run on a laptop. Nothing is computational heavy here. So this is a very small convolutional network, and we download MNIST data set. You can go through and run all the cells. It should be working. And in the end, you get an accuracy on the test data of 98%. Then we deliver the attack, and the attack works in a very sneaky but clever manner. The idea is that we want to change, so let me go back to the idea here. So the idea, we want to change by a certain amount, which is this epsilon parameter here, the original input, and the epsilon controls how much noise you're adding, and the more you add, of course, the more is visible to the human eye. The interesting part of this is that it's actually very easy to implement, because all we need to do this, the sign of the gradient is essentially cleverly selected to fool the optimization, because this is essentially taking the sign of the gradient, which is the opposite of what the optimization do. The optimization normally goes in the opposite direction of the gradient because we're minimizing things. Here we want to maximize, and so we want to fool the optimizer. And so we're getting the gradient. And PyTorch makes things very easy to do, actually, from an API point of view. So once we have the prediction on the test data and we run the attack, what we do is, if the prediction is already correct, is already incorrect, it's fine. We skip it. Otherwise, we take the gradient of the data, and so we run the attack. It's a very simple function implemented by an epsilon here, and then we rerun the model using the perturbed data, and then we essentially calculate the accuracy. And if you run this attack with an epsilon of 0.5, what you get in the end is just 94%. So you're already ruining the accuracy. And this is the adversarial example 5 of adversarial example generated. So for example, this was originally a 6, has been predicted as a 4. This was 8, predicted as 9, and so on and so forth. This is just with one epsilon value. The exercise then tells you to try different epsilons, and in the end, also seeing how can you detect the fact that these epsilons have been tampered originally. So the expectation is the bigger is the epsilon, the more the damage on the accuracy, but also the bigger the epsilon, the more you identify the fact that that's a perturbed and changed data, essentially. You can you can run this on your own. It's not absolutely important if you don't. And this requires some time. So if you don't mind, I can just close this on this point and then move on to the next one, unless you have particularly interest or curiosity about this. Okay. Anything from the online audience? Yes, go ahead.
Is there any way to use these adversarial examples in the training data set?
Yes, yes, that's a very good point. So the point is there any way, should I repeat it for the online audience? Okay, yes, the question was about, is there any way to use this knowledge of adversarial example in a clever way to counterattack? Essentially, this is what you're asking, isn't it? So how can you, now that you know there's vulnerability, what can you do? And there are plenty of things. The short answer is yes, you can use the adversarial examples. The thing is, we're not talking about countermeasures. We're just showing you, in this case, vulnerabilities. But of course, the next step would be, okay, I should do something about it. Yes, very good point. Let me just move on to the model inversion attack, which is way more interesting, and actually even more intriguing to do, and very quick. So, the reference paper is this one, Model Inversion Attacks that exploits confidence information and basic countermeasures. I've re-implemented on my own 2 of the 3 models presented in the paper, and the experimental settings we've been using is exactly the same of the paper. Good. So, let me just show you what's going on here. So, the very idea of this, the first thing is we're going to train a model to recognize faces from the AT&T faces dataset. I wrapped this up into the PyTorch dataset object, and this is called all faces, and you should be able to download it and on your machine and get it. I don't get the download because I already have it on my local machine, but this should start to download and to get it. If you have troubles, let me know. Then we set up the data loader. Okay, a few notes about the dataset. The dataset contains 400 images of files corresponding to 4 different subjects, 10 photos each. Each photo is that dimension and grayscale, and is taken at different times, varying the lighting, the facial expression, open, closed eyes, smiling, serious face, and the facial details. The train test partitions I applied in the training is exactly the same the authors are using in the paper. We might argue this is not very clever from a classification standpoint because this is not very good partitioning actually, but for the sake of the model inversion is very clever. What the paper is doing is randomly pick for each of the subject 7 faces out of 10. Those will go into training. The rest, the 3 remaining ones, are going to the test set. All right. Of course, from a classification point of view, it's not very clever, but this is what it is. Good. Okay, so let me just show you these faces, and also have, so this is example faces from the dataset. Let me also show you another note, which is a sort of a question for you. Would you please run this and also tell me that you see exactly the same face? Those are randomly selected because I skipped this, but I should focus a little bit about this. This is taken from the training loader. The training loader has the shuffle set to true, so they're randomly taken. And when I run this, you should have exactly these faces. Do you? Yeah. Brilliant. Anyone having any guess on why this is happening? Yes, it's very up. And this is just the side information I want to give you. Always remember to fix the seed when you're having random things, basically all the time. So if you really want to make things exactly the same, regardless of the machine, fix the seed and you'll be there. So that particular case set the seed to NumPy and Torch, and this is the reason why you're having, despite the shuffling, you have exactly the same faces displayed. Good. So if we move on, I already implemented the softmax. So the models in question are very, let me say it again, very simple. It's called softmax regression, and as an extension to logistic regression. It's 2015 paper, so the terminology is not super up to date to what we have now. And then is multiple layer perceptron. And let me just show you, the learning rate is just 0.1. Let me just show you what I mean by softmax regression. This is the model. It's just one linear layer ending up with a logarithmic softmax in the end. So we do train this model, and then we save it. We save the best model here. You can run this, it's very quick. You can also run the MLP if you like, but is essentially taking more time, so I'm not going to do it. I already saved the checkpoints, and you don't need to run this if you want, because later you can download the checkpoints already. So ultimately, this model is going to have a 94% of accuracy. The multi-layer perceptron is going to be slightly better in classifying faces. So again, the classification deal here is to classify which is the subject the face is belonging to. Very simple. Oh, by the way, this is the best validation accuracy we got. And so this is the model we've been saving as a checkpoint. Good. You can run this. You're not really required to do that. And the multiple layer perceptron is a linear hidden layer and the prediction layer, like that. Now that we have the having here is that you're using models as from an API. You're not having any knowledge about the model, you're having any knowledge about the data, and you don't know anything at all about the model. It's a black box. In fact, this particular kind of attacks is called black box testing. Black box attacks. You don't need knowledge about the internals of the model. You just use the model as a black box. So far, so good? Just keep the watch under control. So now the point is, we have the train model. We want to deliver the attack now. So in this notebook, essentially, we're saying you can skip completely the training. It's really not important. You can just reload the model on the best training. This is exactly what we're going to do. So let's try to run torch. Okay. We get the data set. So this is the size of the data set, 280 samples in the training, 120 in the test set, summing up to 400, all makes sense. And we get the training data, which is the big one. Good. Okay, let's deliver the reconstruction attack. And so let me just show you first, where is the attack? Oh, it's probably downstairs, isn't it? Right, this is the idea of the reconstruction attack. Very quickly, the thing is, we want to pass in the label we're aiming for, just the class. So the only piece of information we need is that we are dealing with a classification problem, and we're dealing with some classes identified by numbers, essentially. So 1, 2, 3, 4, depending on what that might be. And then we pass some parameters which controls this attack, alpha, beta, gamma, and lambda. Lambda is a learning rate. Alpha, beta, and gamma essentially are some threshold. So alpha is the total number of iterations we run the attack up to. Beta is the maximum number of iterations without any improvement. This should be without improvements. Gamma is the threshold of the cost. So the maximum number of loss we can calculate during the attack. And this is the very idea. So this is the general attack. For this particular case, we're not using any auxiliary term. So this is just to emphasize we're not using any external information. So the auxiliary term in the original paper is specifically to refer to any additional information you have on the attack you're dealing with. All right? We have no clue whatsoever what's going on. So this is just to highlight that the initial cost is the cost generated by the model. So it's the actual prediction of the training model. And then we keep on going up to alpha iterations by processing the data we get from the model and trying to optimize the generation of these tensor we're creating by knowing which is exactly the label the model is producing. This is the information we're actually stealing from the model. So we're getting the prediction from the model as a black box, and we're using that using the optimization in the other hand. So let me show you this in code. So we start with a tensor of 0. This is the mi-face implementation attack. Yes. We start with a tensor of zeros, so absolutely nothing, which requires gradient because that's the trick. We start with a model which is being pre-trained, and so we get the prediction from the model, actually the full tensor of logits here. Then we set up a loss for the attack, and we iterate up to a number of alpha iteration. We reuse the model. We zero the gradient of the tensor we're modifying, and then what we get the target class generated by the target class is the one we're aiming to, so the one we want to steal, and we calculate the loss between the prediction and the target class, and then we use a sort of a stochastic gradient descent optimization on this tensor. So the last bit is this process function, which is very generic. Actually, is not doing anything at all. This process function is just normalization between 1 and 0. It's like dividing by the maximum. So is the tensor minus the minimum divided by the maximum minus the minimum. It's very normalization. And I'll tell you a second what's the effect of this normalization. And we keep on going until some sort of threshold of optimization has been reached using purely stochastic gradient descent. That's probably another thing I should say. In the original paper, they're using gradient descent. I'm using stochastic gradient descent, but essentially the same thing. So this is the attack function. Oh, I didn't want to spoil you anything. Sure, let me just, for a second, let me just clear the output here. Sorry, I didn't want to.
So the gradient you compute for the attack you do on the cost function that NNL loss that you define specifically for the attack.
Very good
right?
point.
So
yes.
You don't need to know the cost function of the original model. Right?
Not at all. The model is actually a black box. That's a very good point. Yes. Let me just rephrase this. This is a very good point. So we are creating our own criterion, which is the classification loss, but the model is being used just as a black box. This loss, which is this one here, is between the target class and the output generated. And so we're trying to identify what is that the model is actually producing. And if we run the attack on this very simple model, that's because I haven't run everything. Sorry about that. Let me just redo it. This is the pre-trained model, functions, and let me find it. So we start with an empty thing, of course, and this is what we end up with. We're just after one iteration. The reason for this is because the model is overfitted, of course. And in fact, there's an extension paper. This is in the slides, to be honest, the reference to that paper. There's a follow-up paper after this saying that there's a direct connection with model inversion attack and overfitting. This particular model is very overfitted, and so you just need one iteration to steal this kind of information. So just without any knowledge of the model, we've been able to reconstruct some information that has been used to train. And so this is still an example, but you have to imagine that things might get really complicated and even worse if you're using sensitive data. I hope this clarifies a little bit the importance of doing this sort of things. Is there any other question? So I can keep going. By the way, another thing I should mention here is that the quality of the reconstructed thing is not very high just because I didn't do anything. I just applied normalization. That process function is just to do some sort of normalization to the data. You can, in the paper, they're using a technique which is called, is a normalization of images. I can't remember off the top of my head at the moment, sorry. But they're cleaning, so to speak, they're normalizing the results so that they can look more clear and more evident what's going on there. Very similar to what I showed you in the slide earlier. And I tell you even another thing. If you're now intrigued by this, and this is just starting, let me just rephrase a little bit this. We're just taking the first 10 class out of 40, and what we're passing to the model is the pre-trained model and the class we should aim for. So I want class number 0. This is what we're saying. Okay? And as you can see, is always like, we have no clue whatsoever what's going on, but all the time is a different phase. So we don't know exactly if that phase will correspond to the actual class, but nonetheless, we're stealing sensitive information within the model. This is called model memorizers and stuff like that. So if you're intrigued by this, you're very welcome to try the second bit of the exercise. If you want, I can give you 5-10 minutes if you like. And run this with a pre-trained multi-layer perceptron. That will take a little bit more time on your laptop, presumably. It did on mine. And the code is very similar. It's actually the very same thing. But you will see that the quality of the reconstructed images is even better with exactly the same code. And this is because the model is more complex, and so more parameters, and so more space for memorization. That's the takeaway message, I'd say. Do you want to do this exercise and try it out? It's really copy and paste from above. I can do it with you live if you like. So MLP, we instantiate MLP, we get the weights from this link. I should probably have it already. Let me try the luck here. And all I have to do, yes please, thank you. All I have to do is to get the code here. There you go. We load the weights. This time is called MLP model inversion attack. This should be MLP. And then we print MLP. That's the model. Brilliant. Now for CL in range 10, MI face, MLP, CL. What? Yes, sorry, typo here. Good. It's taking a little bit more time, but as you can see, something is different, and sometimes it requires more iteration, so it keeps on going. This has taken 152 iterations. That makes sense, actually, because the model is more complex, so the optimization has more parameters to optimize. But they're not the same. So in some senses, it's actually even better quality. And there's plenty we can do, but nonetheless, we're leaking information the model has memorized. Okay, was this convincing enough? And again, this is not generative model. Good, so let's see what we can do. Good, so maybe, in the interest of time, since we are talking already about model inversion attack, let me just use a different order of topics I had in mind. And let's just keep now to the part number 3. So all of this, I don't have to repeat things because you already have it very fresh. And let's move to the differential privacy bit. And let me just introduce you to Alpacas. First things first, if you're looking for a very nice reference, I found this book online, which is online and totally open source in terms also, not just the source of the code attached with the book, but also the source of the book. It's really wonderful. It's called Programming Differential Privacy for Programmers. So it's exactly what I was looking for. And it is very, very interesting book. From the book introduction, it says, the book assumes a working knowledge of Python, as well as basic knowledge of the pandas and NumPy libraries. You will also benefit from some background in discrete mathematics and probability. This is all about. Basic undergraduate course in these topics should be more than sufficient. And these are the references you'll find in the notebook. It's very, very highly recommended. And the striking things for me was also that the logo of the book was programmed in Python, which was brilliant. And this is the logo of the book. And if you're up to a shameless plug, I already had a small section of the first chapters from this book in another tutorial I gave, which is called Privacy Preserving Data Science. And in particular in the section of programming privacy, you'll have notebooks explaining you the difference between moving from k-anonymity to differential privacy. You'll find it there. And then, in this section, we're finally introducing Alpacas. Alpacas is the PyTorch framework for differential privacy. And if you're wondering what Alpacas is a new high-speed library for training PyTorch models with differential privacy. That's more scalable than existing state-of-the-art methods. And in fact, it is. Differential privacy is a mathematical rigorous framework for quantifying the anonymization of the sensitive data, and it's often used in analytics with growing interest in the machine learning community. And let's have a look at how Alpacas effectively works. And to do that, I'm opening the link pointed here, introducing Alpacas, which is pointing to an article on the Facebook. This is from a group from Meta, so from the Facebook research. And the reason why I'm here is because there's wonderful animation which is really nice and gives you the idea of how Alpacas works and where differential privacy is used. So essentially this goes like, okay, I have a normal training loop, and you start from forward pass, and so you get parameters on the layer 1, the layer 2, you calculate the loss, and then you back propagate. And normally the way you do it, you go layer by layer in the backward direction, and then you update the parameters on the optimizer. The way Alpacas does is that whenever you have to do this optimization, the value in the backpropagation are clipped, then aggregated, some noise is being added, and then those parameters are then used in the optimization. So to make it very simple, the idea is that you can add noise during the optimization to the gradient, so that the model won't retain any information, because it's going to be, and the way, of course, the noise will be added, it's according to the differential privacy strategy. Okay? So long story short, the model will be trained on perfectly, cleverly perturbed data with noise, so that the model won't memorize, presumably, and no privacy information will be leaked. And if you're not believing me, which is fair enough, you might want to see it in action. So let's now train the very same model, softmax regression, using Alpacas. And I think that the most remarkable takeaway message from this notebook is how easy it is to do it, and how less is impacting the existing code. In fact, I can import the same things, and hasn't changed it. This is actually copy and paste from the previous notebook. Is just creating the data set. I'm not doing anything fancy here. Same data set again, blah, blah, blah. Again, same faces because the seed is fixed. Good. Now, setting up some parameters for the differential privacy. So the maximum of the gradient norm, the epsilon makes sense for the differential privacy, is the epsilon of differential privacy. and the number of epochs we want to train the model. Rule of thumb, with differential privacy, it's recommended to increase a little bit the number of epochs you want to train your model, because otherwise you're not presumably getting the same performance. By the way, something I forgot to mention is that, yes, we're going to train the model on this noise mechanism in order to not leak any information. But of course, we don't want the model to worsen the performance too much. So the deal is, we want to change the model to save privacy, but at the same time, we want a model that works. Otherwise, it doesn't make any sense. Okay? And so, rule of thumb, just increase a little bit the number of epochs. So, importing the same model from the same module, creating softmax regression. Alpacas comes with this validator, which says there's no errors in this model. If you look at the tutorials, this is showcasing you on ResNet, and essentially this is just to tell you that sometimes some models using, for example, using batch normalization, apologies for that, contains layers that are not very compliant with differential privacy, so you cannot apply differential privacy on batch normalization. So it gives you warning saying you should change the model. Actually, also in addition to give you warning, it also comes with utility method that fix your model for you automatically. That's very brilliant. So again, same learning rate, same model, okay. And now it comes Alpacas bit. So from Alpacas we import privacy engine. And the privacy engine is this object which we instantiate here. And we create this privacy engine by passing in the model we want to optimize, the model we want to train, the optimizer, the data loader, and the number of epochs, and all the parameters needed for the differential privacy. We run this, which of course is not working because I forgot to run something else. And I apologize for that. Let me just do it again. Okay. Now, I have everything on my hand. So I have this softmax regression, which is a new model with differential privacy. I have the softmax SGD, which is the new optimizer with differential privacy. I have the new loader with differential privacy. The loader is also passed in because there's a new feature they added in to add some different sampling from, which is also another thing we might want to talk about extensively from privacy preserving perspective, but just take it for granted for now, is not really the point. And now I am importing the very same function, and I promise you, it's the very same function from the same module, the same Python module, so the same train function I defined before. And I didn't show you this because it's really boring. It's just like the normal training loop in which you have iterate over the different epochs, and then if you step the model, and the step, if it's training, you stop the gradient or not, blah, blah, blah. It's the same thing. It's nothing particularly interesting here to see. So I'm importing the very same train function, but this time I'm passing to this function the privacy preserving model, the privacy preserving optimizer, and the new loaders with differential privacy. And I run this, and it works. I hadn't have to change any bit in my code. So if you remember this very highly overfitted, so I won't expect 98, 94, whatever that was, accuracy on this model, but let's see where we go. It's taking a little bit more because there's more epochs, and there's much going on in the back end, of course. There's much more computation going on. So, of course, this is affecting a little bit the computation time as well. What time is it? Good. You have a good half an hour to do the rest of it. Fair enough. While this is going till the end, do you have any question, curiosity, any feedback? Please go ahead.
I'm kind of surprised if you compare this just to stochastic gradient descent, where the individual batch components are selected stochastically. So just the fact that now you're adding noise at a different stage, right? Not in the selection of training batches, but rather in the vector of the gradient itself, right?
Yes.
So I'm surprised that
This is going to work at all.
yeah.
Okay.
I mean,
Good.
so first of all, why doesn't stochastic gradient descent itself introduce some kind of privacy, or maybe I should ask, does it introduce privacy, and does the optimizer that you use change the privacy of the model that you learn?
Essentially, the algorithm which is in the back end is called differential privacy stochastic gradient descent. That's a very good point. And this is the algorithm they designed to create Alpacas. And the strategy of adding noise to the parameters during the optimization is what differential privacy stochastic gradient descent is doing. I just showcased you with the animation to give you the idea of what's going on. The documentation is very thorough, so you can actually find more details there. Long story short, the sampling and the methods of noise is being added during the optimization is not just random noise. It's just very selected noise using different mechanisms. The most popular one is Laplace, is in differential privacy. But there's extensive literature in that, actually. In the meantime, no, thank you for the question. Just a second, I'll come back to you. So we have a 71% of accuracy, so of course degraded. I don't know if we can keep on going, if we have any better accuracy, but fair enough at the moment. This is what we have.
Doesn't the noise being added during the backpropagation become some kind of a private key then? If you have the noise added, you can rebuild it?
That's a very good point. And that's the reason also why Alpacas is applying a specific sampling on the data loader as well. Because the data selection during the training, given a limited amount of things you can do, especially with shallow models like this, might be leaking some particular information. Yes, that's very true. So I'm showing you this as a black box, and I promise you there's lots going on in the back end. And documentation is fairly acceptable, in my opinion. But of course it's open source, so you can contribute, and I'm personally willing to be honest. So now the thing is to close this block. Now that we have the model, let me trust this notebook, no, it's not trusting me. Now that we have the model trained with Alpacas, we can see if this had any effect on the model inversion attack. So, calculating, instantiating the Alpacas pre-trained model, redoing the same thing, MI faces, and running the attack here. And this is what we get. Absolutely nothing at all. So the same attack is not being able to reconstruct any sensitive information here. And you can keep on going, you always have the same thing. Okay? Does that convince you a little bit? Yes, please.
So you mentioned that the models are often overfit, so that's why you can construct those images?
Yeah.
So if you do the decent regularization, how would you expect the images to change?
Brilliant question. If you look at this, what we're doing is essentially a form of regularization. So indeed, that's, for example, why batch normalization is not required. That's why you typically don't do any extra regularization on the model. Differential privacy is already a regularizer to the model, indeed. Yes, very good point. Thank you. How do you mean?
If you were to put dropout in your original model, does that make it harder for the gradient attack?
I can't remember off the top of my head what's the role of dropout is. That's a very good point. I can't tell you right now. I have to think about it. But that's certainly something I should remember for next time. Thank you for the questions. They're brilliant. Any other feedback question on this part? Just out of interest, has this worked with me showing you the attack and then the solution? Okay, I should probably change the structure later. Brilliant. Okay, so now we have sort of 20 minutes, and let me just now show you something we can do with federated learning, which is the last bit I wanted to present to you. So let's introduce federated learning very quickly. Federated learning is, to be fair, one of the most intuitive things in this scenario. And despite the fact that, again, you have multiple clients contributing to one big cloud of server, which is aggregating the things and then distributing the updated information. So I didn't explain clearly how federated learning works, and the very idea is that the standard representation of federated learning is every single client has its own data partition and their own model. So every single client has capacity to train a model locally on their own data, and then every single client communicates on a secure channel with this cloud, which is gathering all the different gradients, if you're using gradient-based methods, is gathering the multiple gradients from all the clients, averages it, which means that it's taking into account all the different clients, and then distributes the updated gradients back to the clients. So that in the end, every single client will have the updated model, which has considered implicitly the data from the other clients through the aggregation. Does that make sense? This is a standard representation of federated learning. To be honest, there are two things that nobody tells you initially, and I think they're actually paramount important. First is that to make all this to work, to have everything to work here, and to make any sense, the features you're having in this scenario should be the same for all the clients. So, and technically speaking, this is called horizontal federated learning. The idea of horizontal and vertical, of course, because if you have horizontal, there's also vertical federated learning, is that imagine the classical representation of data in machine learning. You have samples and features. So you have the matrix of samples and features, samples on the rows and features on the columns. If you have horizontal federated learning, you're essentially taking this matrix and slicing horizontally. So, which means that the features are the same. So the columns in this data set are the same. Just the rows will be split through the clients. Okay? This is horizontal federated learning. Vertical is the opposite. So you have the same set of samples from multiple clients, but each client has different set of features. And if you're wondering whether any of this scenario is real, you might think of, so the case of mobile phones is the case of horizontal federated learning, because it's the case of we're having the same features, but different samples in the data set, okay? The case of vertical, on the other hand, is as well realistic. Imagine that you're having some fancy health data set you're allowed to use from one hospital, but another hospital is holding labels. That's the typical example of vertical federated learning. So you have one client or one node in this network holding the piece of information relating to the labels, and another client holding the piece of information about the features. And you can keep on going, actually. You can have one data set containing some set of features, another data set containing another set of features, but still the same subjects. Does that make sense? This is vertical federated learning. We're going to see an example of this.
I have some questions online. Should I?
Go ahead.
Okay.
Thank you.
Are there any metrics to measure privacy, or how can one measure privacy achieved?
Could you repeat the question, please? What was the first?
Are there any metrics to measure privacy? That's the first question.
Are any metrics?
Yeah, to measure privacy.
I
And then-
don't understand what you mean by measure privacy.
Yeah. Or how can one measure?
Measure.
Measure. How
Okay.
can one
Sorry.
measure privacy achieved?
I'm not entirely sure I got what you mean. Sorry about that.
Maybe like probability or identifying something you have tried to.
I'm puzzled by the use of metrics.
Matrix.
Yes,
Matrix.
metrics. Yeah.
So I think the question is there any way for you to be able to measure maybe the level of success or failure achieved in the privacy you are looking at?
Oh yes, certainly yes. There are tests you can run on your data to see how much information you're leaking or whether. Yeah, I skipped this part and I appreciate the question. It makes sense actually. And this, if I understood correctly, this goes towards the data anonymity thing, as in how much information we're releasing. And this is the very idea of k-anonymity, for example. So k-anonymity is built on the idea of how unique is a record within a data set. So how easy is to spot one, and is not just about one single column of value, it's also the aggregated columns. So for example, if I have in one data set the only one sample which is the only representer for one specific set of combination of values for 3 or 4 columns, that is very identifiable, and this is what k-anonymity tries to solve, I think. In case there's the section about privacy, data science I mentioned before as a reference.
There's a question here. Could you compare differential privacy with federated learning at the end again? And then they follow up. When should when should one be used against another?
Absolutely.
Or which one would you prefer?
Yes. So this is a very nice question, and to be honest, I haven't provided answer to that yet because I haven't specified what differential privacy, what federated learning can do. I just showed differential privacy, to be fair. Although the two things can be combined, and federated learning is just a framework that you can use to in combination with other things. This is differential privacy. Federated learning is another framework in which you're essentially having multiple actors in this communication and involved into the computation. If you're having data set with one single silos or database, you don't need federated learning. Essentially, federated learning is coming into place when you have multiple actors, so multiple data owners or multiple silos of data you want to access. This is, and of course, you can combine federated learning with differential privacy. The two things don't go separated. But federated learning has also some sort of cons. So first things first, is federated learning similar to distributed computation? Too long to read? No. Client devices have limited network bandwidth in case of on the phone examples. And there's also another deal in federated learning. The different nodes holding the data, since they're owner of the data, they also should be allowed to do computation on this data. This is a major, huge requirement federated learning is imposing, which sometimes may not be attended. Something like, you're the hospital holding the data. I won't never access those data because I'm not allowed to. I just want to set up a framework to do computation on this data. So I just want you to send me the result. I'm asking you to calculate. But at the same time, and that's the deal, I don't want you to steal my calculations because it might be my ownership. IP. Yes, thank you. That was looking for. That's my idea. So I have my solution. I don't want to leak my solution to you because I might be giving away information, private information as well. Not data information, but private information. And so this is the deal with federated learning with encryption. The encryption and the privacy preserving should be guaranteed on both ends. This is very roughly. And so this is where we're going. Yes? Is 10 minutes? Oh, you're right. Thank you. Fabulous. So I think I already answered this question. So homomorphic encryption, I told you already what's the deal with it, and I probably also give you why you want to do that. So homomorphic encryption, again, enables computation on encrypted data without decrypting the actual data. And moreover, any operation made on ciphertext generates results that, when decrypted, correspond to the result of the plain text, which is amazing. We're going to see an example of that in a second. And as you may imagine, this is going towards the, I don't know why it's not trusted here. This is going towards the cryptography field. I'm not touching it, not even close. But there is a huge literature about it. And I will give you in a second a very nice reference to where you can go if you're interested in exploring more about this, everything I've told you today before closing. So what we're going to do here, we're using a package in Python which is called PHE, standing for partially homomorphic encryption. And this example has been actually adapted from what has been found in the repo. We're doing logistic regression using homomorphic encryption. Nothing particularly fancy here. We're using Wisconsin breast cancer dataset. We're also taking a context timer to see how long it takes to do computation. We have its security bit, so again, Alice and Bob. The lack of fantasy here is overwhelming. We have Alice, which has some model, which is the logistic regression model. And then Alice is the one holding the public and the private key. So Alice is the one who's in charge of decrypting things. And Bob will be the one having to get the public key from Alice and using this public key to encrypt whatever Bob wants to encrypt and send it back to Alice. So in fact, we do get the weights, and the intercept is just like the parameters of the logistic regression. And we use the public key to encrypt the parameters of the model. What I was looking to is this. So we generate the pairs of keys here. And then, let me just run this so it makes more sense very quickly. So this is the data set, this is Alice, and so Alice has the model, which fits the model on some data, makes prediction, and encrypt the weights. Yes, that's the bit. There's Bob. So we have data set with some robust scaling normalization. We initialize Alice, and so Alice generates the key for Bob to receive. And then we have Alice fitting the model, which takes some time, so it's 0.2 seconds, very quickly. And so this is just to test the model performance on the test data to see how it works with unencrypted data. And this is it. And then now Alice encrypts her trained model parameters. So we have the weights and the intercept. So we're sharing now with Bob the information about the model. So Bob takes the public key Alice holds, which is the one Bob needs to use to encrypt the thing Bob is calculating. And so essentially Bob, what he's doing is taking the parameters from Alice, updating according to his own calculation and giving it back to Alice. This is the deal. So set the weights with the one encrypted sent by Alice. And then we calculate the encrypted value, which takes some time, on the test data, by the way. So it's running on the test with the encrypted value. So I'm using the encrypted model from Alice. I'm not using any model on my own. And then Alice is able to get the scores from Bob and decrypt it, and leading to this error in the prediction. So this is just a very simple example to showcase how homomorphic encryption actually works on making basic computation like standard machine learning computation. And the computation we're doing here is logistic regression, so very basic. If you wanted, there's a more extensive example in the end showing you how to implement further learning and homomorphic encryption in this other notebook. Before wrapping up, I want to show you two things very quickly. One is the plug about resources I promised you, and this also connects to OpenMind, which is this community I reached out to last year and a half, which is very active in the context of previously observing machine learning and defining many tools in this context. The most popular one is SIFT, or PySIFT, which is now at the version 0.6. And OpenMind is offering the private AI series courses, which is totally for free, online. These are the courses which have been produced so far. And Foundations of Private Computation is where I adapted part of the materials in this section, which unfortunately won't have the time to go much into details. I should better calibrate for the next time. Apologies for that. But I'm going to showcase very quickly before the end. And also introduction to remote data science is the latest course released end of last year, in which there is the new version of PySIFT 0.6, which is slightly better from the version you will be seeing in this repository, which is using a completely redesigned mechanism for privacy using what is called AutoDP, auto differential privacy. So it's very focused on differential privacy and allowing to do computation using the same framework I'm going to show you in a second, which is based on further learning and encrypted communication. The example reported here is called Duet. And Duet is the first prototype they developed to showcase how you can do data science on data you're not allowed to see. To do that, you have to have two notebooks. We'll be pretending we're being on two different platforms. You can actually be on two separate machines, but I'm showcasing you here on my own laptop. So I'm doing the client and the server essentially. So at the same time, the data scientist and data owner. But let me just close some things. Otherwise, it's too much. I just want to keep the reference open for later to OpenMind. So, pretending I am a data owner, I have SIFT, and I'm launching Duet. I'm launching Duet, so now there's some server running on the Open Grid network, which is another package, now integrated in SIFT, and this is waiting for someone to join in. I now move to the data scientist notebook. So the data scientist is the one who wants to do data processing on data they don't have. So I'm open SIFT, and, oh, sorry, this is data owner. I messed up. So this is data owner, which is the one that should run first. So I am the data owner, waiting for connection. Okay. And this should be already connected because data scientist now is connected. Brilliant. So now data scientist and data owner are connected. The data owner should make some data available. So in this case, we're having the Iris dataset, the fanciest example I could think of. We're having data split, nothing interesting here. Normally, data can be any format. If their torch tensor is way better, so they're ready in the form they want it to be. So we convert the data in tensor, and then we put some description thanks to PySIFT, which is extending torch a tensor, adding tags and description, and then we can put the data to the data store. And this is the data store. We have a data set of data and target. And to make things very easy for computation, we're just setting to accept from the data owner every possible request. In the very top of the notebook, there is reference to the original notebooks where these things have been adapted from, and you will find extensive examples about this. But again, this is part of the private AI series course, in particular Foundation of Private Computation. To finalize, now I am the data scientist. The data owner has made some data available for me and is accepting any request I'm making. So he's trusting me totally and completely. So first thing is, let's see if the data set is available. I can read the data. I can access this data set from the store. An important bit to mention here is that we have pointers. We are not having data. We just have pointers to some data we don't know anything about. We just know the tags, we know the description, and we know the type. Nothing else. I'm running out of time, so I make it very short. Essentially, what we're doing is to define a torch model here, which is slightly different from the standard torch model because it's a SIFT torch model, which essentially needs to have reference to the remote torch reference in the data owner bit, because this model is being created from the data scientist and then sent to the data owner to do the computation. This is the deal. In fact, we do create the model here. It's a local model, but then, sorry, I forgot to import torch, but then we send it to Duet. So now the model becomes remote. And so if you keep on going, I don't want to steal any more of your time and to your lunch, you can do all the computation considering this pointer to the remote model, and you can actually run it. And this computation, which is now running, is actually running on the data owner end. So while this is completing, essentially what I'm doing is getting some data. So I'm passing in the remote model, the remote torch, the optimizer, which is local, and the data pointer and the target pointer. So all these pointers are actually living in the data owner end, and the data scientist is using it to do some computation, which is going somewhere actually. This is performing some regression. And then this notebook goes like you can download the model and do the test on your local data. So this is one example. The other one, not having the time to talk about, unfortunately, is another case of, and I'm wrapping up with that, is split NN. Split NN is the next steps in further learning, which is about, I'm not just splitting the data, I'm also splitting the computation of the models. So I may have some part of the network living in one client, some other part of the network living in another client, and we're sharing the gradients and finally aggregating all together, and Duet allows you to do that. Please feel free to complete this notebook. They're quite easy to do, to go on your own, I think. For any kind of issue, problem, feedback, suggestion, feel free to reach out. I will be really appreciative. And thank you very much for the extra time and for being here.